4.5 is on the superposition principle. So let's take a look at that. First, we'll just talk about Theorem 3. So Theorem 3 states this concept. If y1 is a solution to this differential equation, a y double prime plus by prime plus cy equal to f of x. And suppose y2 is a solution to same left-hand side, a y double prime plus by prime plus cy equal to g of x, then for two arbitrary constants in the reals, so k1 and k2 and r, the function k1y1 plus k2y2 is a solution to this sum. So is a solution to a left-hand side the same, y double prime plus by prime plus cy equal to k1 f of x plus k2 g of x. So to show that, it's really just some algebraic manipulation. Let's look at the proof of that. So let's then suppose y1 and y2 are solutions to that. Suppose y1 and y2 are solutions to those above. I'll just label them. So this will be star, and we'll do it in different colors just for fun. This will be double star. So it's solutions to both of those. Didn't really have to do all that, but whatever. Respectively. And then we need those to be reals, so we let k1 and k2 be real. So just real constants is all that's really stating. So now we substitute into the left-hand side. So we substitute k1 y1 plus k2 y2 into the left-hand side of the equation. So you get a, and then basically I'll go back up here. We're going to substitute these. Let's just use this. So where to go? So this whole thing here is going to be substituted for y double prime y and y. And so you have to expand it out using differentiation and simplify it. So you get a times, and then it'll be that all of that, k1 y1 plus k2 y2 double prime of that whole thing, plus b times same thing, k1 y1 plus k2 y2 prime, plus c times k1 y1 plus k2 y2. Okay, and then we basically expand and rearrange terms. So when you differentiate, we're not going to simplify anything other than if you do d dx of all of this, you do it each term at a time. So each term, well, not this one, but each term gets the differentiation, and it's just a constant times y. So you're not doing any chain rule or anything like that. We're just going to say basically the y prime. So you expand and rearrange, and you get this form that this is equal to. You get k1, and then you get a y1 double prime plus b y1 prime plus c y1 plus k2 a y2 double prime plus b 2 prime plus c y2. So you distribute a to each term, b to each term, and then this becomes double prime here. This is a prime, this is a prime. That should be a k, shouldn't it? Right there. So that's a k2. And then same thing here, you distribute to each, and then we are collecting the y2's together, so y2, 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 and then factoring out the k2. You factor out the k2, k2, k2. So that it's not that bad, just expand it out and you'll get that. And so that is basically then equal, since the original ones are solutions to these two here, then that must equal k1, and then this, of course, is just your f of x, and that'll be your g of x. And that's it. So you get k1 f of x plus k2 g of x. Okay, so now I'll state theorem 4, which is the existence and uniqueness. I won't go through the proof of it, but I want you to be aware of all these different methods have basically the solution exists, which we kind of already show that, and then the solutions are unique given the initial conditions. And so that's kind of a theme I want you to see as we go. So I'm going to state this. This is theorem 4. And that's what this one is. Again, we've done, of course, a couple of these. So this is existence and uniqueness. So first, we're going to let all of these be constants. So A, B, C, T naught, capital Y naught, capital Y1 are all real. And A is non-zero because it's what's in front of the differential equation. And suppose Y particular, so yp of t is a particular solution. So is a particular solution to a y double prime plus by prime plus cy equal to f of x. So these, and I might have failed to mention this, these are not homogeneous anymore. We are assuming it's equal to a function of x, or could be a function of t, or whatever the variable is for y. Now we're saying it's a function of something. So that's one of the big differences we have, which we did a couple special cases in 4.4 on the non-homogeneous equations. So this is another way to solve that, basically. Okay, where was I at? I got sidetracked there for a second. So So there's your f of x. So that's true, or that's your, you have a particular solution to that equation in an interval. So that's where I was at. So in an interval I with t naught in I, y1 of t and y2 of t are linearly independent solutions to the homogeneous case. Okay, so that's your assumption. Well, in I, so that's our assumption. Then, all right, so just a little recap of that. So we're letting those constants, etc., and we're yp is a particular solution to the differential equation. Okay, we're also assuming y1 and y2 are linearly independent solutions in a homogeneous case in I, which would have got from above. Okay, so if that's true, then there exists a unique solution in I to a y double prime plus by prime plus cy equal to f of t. Y of t naught equal to y naught, y prime of t naught equal to y1, given by y of t equal to y particular plus c1 y1 of t plus c2 y2 of t for specific c1, c2. Okay, so the proof of that, I'll go over, well, I copied it, so we'll just copy it over here. If it lets me. Hello. Copy it. It's not letting me copy. I'll just have to copy this whole thing over, I guess. That's weird. We'll just have to do it like that. Normally it just copies it over. Okay. All right, so there you go. So here's the proof. This is on page 182. It's not that bad, actually. It's just I didn't want to go over every little detail all the time. So when you look at this proof, basically what you do is you set up the solution like before, and then you can solve for C1 and C2 like we did in 4.2. They even state that. And this denominator is that Wronskian again. And we know that's non-zero because we're assuming that y1 and y2 are linearly independent. So that Wronskian is non-zero. And you get a solution. Then to show, here's that lemma we talked about. So why is this solution unique? Well, the standard, what you do to show something's uniqueness, or how you show uniqueness, is you assume that they're two different ones. And you either show they're equal, or in this case, they end up showing that this has to be the trivial case. It has to be zero. So this is not real obvious, I think, but if you have a moment, try to see if it makes sense to you. But that's sort of the standard practice. So you say you have two different solutions of the same form, and then you show something about it. Now in this case, they're not showing them equal. That's interesting. They're showing that that one has to be trivial. Okay, so from here, really just want to show you the different cases and number of examples and how you apply all this. So that'll be next. We will be doing the examples. So let me just write them out. So these is examples. We will do we'll do a few this time. 4, 8, 18, 20, and 28. I think. Did I do all those? 4, 8, 18, 20. I did. May not do them all in the video, but we'll do a number of them, of course.